When we apply a step input to a second-order system, the output follows a characteristic curve. It rises, may overshoot the target, oscillates, and eventually settles. The shape of this curve tells us everything about the system's performance. Today we'll learn how to read and quantify that shape. The first parameter is rise time, TR. It measures how quickly the system responds. We define it as the time for the output to go from 10% to 90% of its final value. A smaller rise time means a faster system. Watch the curve. The steeper the initial climb, the shorter the rise time. Next, peak time, TP, is the time to reach the first peak. The overshoot, NP, is how far the response exceeds the final value, expressed as a percentage. An overshoot of 20% means the peak reaches 1.2 times the final value. High overshoot means the system is too oscillatory. The formula for percent overshoot is e to the negative pi zeta over the square root of 1 minus zeta squared times 100. Settling time, TS, is the time for the response to stay within a band around the final value. We typically use a 2% or 5% band. Once the oscillations decay enough to stay inside this band, the system has settled. The formula is approximately 4 divided by zeta times omega n for the 2% criterion. Let us see all 4 parameters together on the same curve. Rise time captures the initial speed. Peak time marks the first maximum. Overshoot measures the excess above the target. And settling time tells us when the oscillations become negligible. These 4 numbers fully characterize the transient behavior of a second-order system. Now the key insight. All these parameters depend on just 2 numbers: zeta, the damping ratio, and omega n, the natural frequency. Watch what happens as we change zeta. With low zeta, the system is fast but oscillatory, with large overshoot. With high zeta, the system is slow but smooth, with no overshoot. The sweet spot for most designs is zeta between 0.4 and 0.8. We can translate time domain specifications directly onto the S-plane. A settling time requirement defines a vertical boundary. The poles must be far enough to the left. An overshoot requirement defines a wedge-shaped region. The poles must be inside a sector with angle determined by zeta. A rise time requirement pushes poles further from the origin. The intersection of all these regions gives the acceptable pole locations. Let us work a concrete example. Given a system with zeta equals 0.4 and omega n equals 5 radians per second. Rise time, approximately 1.4 divided by omega n, which gives 0.28 seconds. Peak time, pi divided by omega n times the square root of 1 minus zeta squared, which gives 0.68 seconds. Overshoot. Using the formula, we get approximately 25.4%. Settling time, 4 divided by zeta times omega n, which gives 2 seconds. These numbers tell us fast response, moderate overshoot, settles in 2 seconds. To summarize, 4 parameters describe the transient response: rise time, peak time, percent overshoot, and settling time. They all come from zeta and omega n. Low zeta means fast but oscillatory. High zeta means slow but smooth. The S-plane connects specifications to pole placement. In the next lesson, we study steady-state error and how system type determines the error for different input signals.